Welcome everyone, my name is Levente Rácz and I'm an assistant lecturer at Power Electric Department. In this short presentation I would like to present the FARCROSS European Union funded project. The FARCROSS project is in the group of bridge projects, and this is a 4-year project which started in 2019, and our goal is to facilitate regional cross-border power flows. And why this issue is important? Because if we see the energy system, we see the electricity system, we see changing in the producing side and also on the consumer side. So we have to develop our transmission system also. And in this project, we try to improve the power flows by hardware and software technologies and also some market optimization. As you can see, there are different demonstration areas in these projects, and VP5 and VP8 is important because in these VPs BME is involved. DLRH is about dynamic line rating, and OptimCap demo is about market optimization. If you are interested in the results and actualities, you can check the website and also LinkedIn and Twitter. In this presentation, I would like to focus on VP5 and its result. VP5 focuses on dynamic line rating, which is an effective tool if we would like to increase the transfer capacity of power lines. So what we do in this project, we install sensors on power lines, on phase conductors, and also on the structure, and we monitor the weather parameters and also the line parameters. And in this way, from the collected data, we can calculate ampacity and also line rating and also some health indexes on the power lines. In this project, four countries are involved: Hungary, Austria, Greece, and Croatia, and you can see that 8 power lines are involved. So what are our results in these projects? Dynamic line rating sounds easy, but there are really huge challenges. The first challenge is which power lines are good for this technique and where to install sensors. So the first task of BME was to define a sensor placement strategy and do seg model, and we did it for all the power lines, and we found the critical points where to install the sensors. We found during the project that so many sensors and weather stations are needed in the project, so we tried to do some optimization and try to find a way how to reduce the costs. So we developed different algorithms. The first one is an artificial neural network-based conductor temperature model. The core of the model is to install sensors, and after 1 year we train the neural network, and in this way we can reinstall the sensors to different sections. The second one is a novel ampacity calculation approach. This is based on sensor measurements. This is a novelty because in the literature there is only available algorithms which calculate the ampacity from weather parameters. So in this way we can reduce the number of weather stations on the line, in this way reduce the cost. And last but not least, we have an icing alert system, which is really important because in the last 10 years there were more than 5 events in Hungary when tower collapsed and conductor broke, and we have an algorithm which can calculate from weather forecast the typical type of the ice and also the thickness of the ice and the mechanical load of the ice. So in this way we can calculate the preventive current and to heat up the conductor to prevent icing. Thank you very much.